start off by just backing up on calculations and just analyzing how studies might be set up and how we might analyze them, how we might apply. In this particular case, we're interested in a t-test because we've been dealing with comparing means of groups up to this point. Later on, we're going to be doing additional other kinds of tests. During our last review session, we worked on confidence intervals. We went through many different kinds of examples of that and situations with proportions and so on and so forth. So this time, we're actually going to apply some of these tests, these t-tests. And there's going to be several different ways that we're going to apply it. Basic group that we're looking at is that some situations we might take a sample from a population and we might want to compare it to a known value. In a proportion, that might be comparing it to, say, 50% to determine whether or not someone might win an election. In other cases, we might be comparing the effect of a drug from a sample population that received that drug to what we know about the population if it didn't receive that drug, but for which we know we have a mean, say, blood pressure or blood sugar or something like that. So we have one sample and we're comparing it to a known value. So that would be a one sample t-test, obviously, because only one sample is being taken. It's being compared, the result of that sample is being compared to a known value. Most of the time, we're going to be sampling two groups. For instance, in a drug study, we might be taking individuals, some of which are going to get a drug, others of which are not going to get a drug, and we're going to compare the response in those two populations. Instead of a drug test, it might be an intervention of some kind. Economic intervention, a health intervention, a training intervention. Could be anything, but you have two groups. And when you have two groups, we're talking about independent samples t-tests. Group one is population one is being sampled independently and randomly. Group two is being sampled independently and randomly. We have two means, not population means, but means for samples. We have mean of group one, mean of group two. We have two standard deviations. We have a standard deviation for group one. We have a standard deviation for group two. So now we want to compare those two means. So we do an independent samples t-test. Within that group, we have a couple of there's a choice we have to make, a basic choice, and that choice is that that we're going to decide whether the standard deviation or the variability in group one, we know we want to demonstrate that the means are different, right? So automatically we're hoping that they're going to be different, but we have to make a judgment of whether the standard deviation or variability in group one is different than the variability in group two. If we say to ourselves, well, the two variabilities in the two groups probably the same, even though the means may be different, then we have a reason to combine those two standard deviations into a pooled standard deviation. Use that for a t-test, right? So in our first test was single sample t-test, we only have one standard deviation, and that's from our sample usually. In our independent samples t-test, we could have a pooled standard deviation based on both samples, or we could have independent standard deviations, unpooled. And then finally, we might wind up in a situation where we're comparing two proportions. And in that situation, we're going to be calculating our standard deviation on the two proportions, or if it's a single proportion that we're comparing to a known value, on that one proportion. So we'll get to that. We'll be going through that. So basically, what we're going to be doing is we're going to be trying to determine whether the means are far enough apart that we can say with a certain level of certainty, usually 95% certainty, that the population means that they're drawn from are really different. Okay, so that's really what our objective is. And the way we're going to prove that is that, or attempt to prove that, is that we're going to try and determine how often we would get that big a difference between the two means if the two populations were the same. Okay, and if 95% of the time we would not get that extreme a difference, that would be enough for us to say that the two populations are different. That doesn't mean for sure that they're different, but it means that there's less than a 5% chance that we would get that outcome if the that big a difference if the population the means of the two populations were the same. Okay, so I'm hoping, Hinda, I'm hoping that this will kind of like fill in some of that stuff for you. I think we did a little bit of that on the last review session also. But okay, so let's take a look at this. Okay, as a biochemist working for a pharmaceutical company, your job, I'll post these up later on Blackboard as well. But for now, let's read them together, okay, rather than worry about uploading and downloading documents. I have a few examples we're going to work on, and they use fairly sample numbers, so we can just type them in, and we don't have to worry about or calculate them by hand. So we don't have to spend too much time uploading and making sure everybody's got the files, but I'll put them up on Blackboard as well. Okay, let's read this. Working for Somrica, your job is to test new drugs for possible side effects, detrimental and beneficial. The chemistry of this particular new drug suggests that it may have side effects, reducing the tendency towards obesity. They're working with a particular strain of rat that is used in a lot of these kinds of studies. You plan to treat a group of animals over a period of 1 year and compare their average weight to a group of untreated animals. Okay, so we have two groups at this point, right? We have group 1 and group 2. Okay, so now let's take a look at this. Since we have two groups, we're not dealing with a single sample t-test. We have a group of rats from a population that's going to get this drug, and we have a group of rats from a population that's not going to get this drug. So we're going to have a mean weight for one group, we're going to have a mean weight for the other group, and we're going to have a standard deviation of weights for one group, standard deviation in rates of the weights for the other group. Okay, so let's figure out what we're going to do here. Okay, so based on that knowledge, we're going to run an independent t-test. Okay, doesn't matter. Actually, you don't have to worry about sample size. That'll work itself out as you'll see when we do the calculations. In this case, we might have sampled 12 rats, and we might have put 12 rats into one group, 12 rats into another group. So we're going to do an independent samples t-test. Now, one variation of that would be based on what the variability is in the first group versus the variability in the second group. We might pool the standard deviations. In this case, that might happen. Or might not happen if say the weights that the rats that gain a lot of weight, maybe their weights are much more variable than the rats that don't gain a lot of weight. If that's the case, we would do a t-test that would involve not pooling the standard deviation. Again, we'll look at the exact calculations later on, but our judgment there is we're going to use an independent samples t-test, 2 samples. Okay, let's read the next one. Now, after that study is done, it suggests that this does affect weight, but also let me read it back here. But also proved effective and safe in its clinical trials. The drug was designed to treat symptoms that have nothing to do with obesity. The clinical trials didn't focus on that problem. Won't answer the question whether or not the agent is a potential weight loss drug. The company permitted you to test the agent on a group of 12 people with morbid obesity who have signed appropriate consent forms. Okay, we know that since most of you have completed, almost all of you actually have completed the Ethics and Human Resource course, CITI program, you know that there's a health review system that a research review system that has to approve all these studies if they involve humans. So at any rate, in this case, we're going to look at 12 individuals who are already obese, and we're going to test this drug on them. Okay, so now we're going to treat these obese individuals for a year, and we measured their weight on the day that the treatment started, and they're going to follow a regimen of taking this drug and so on and so forth. You're going to be checking up for them. At the end of the year, you're going to reweigh those 12 individuals, and now you have 2 sets of data. You have a set of data for these individuals before they started taking the drugs, and you have a set of data for these individuals after they've been taking the drugs for an entire year. So you have two columns of numbers, just like you had before, two groups of numbers. But in this case, the first data point is the weight for individual one before they started taking the drug. The second data point is for that same individual after they after they took the drug for a year. So you have 12 data sets, but they're actually not independent of one another. They're not they're not independent samples. They're from the same people. So in effect, you can actually look at this not as two different samples, but as a single sample that represents a single value that represents the difference between the weight after minus the weight before. So we're really interested in this case of looking at the weight after minus the weight before to get a number. If the person lost weight, that would be a negative number. If the person gained weight, that would be a positive number. If the person's weight didn't change, that would be 0. So now we have 12 numbers which represent the differences. And we want to know whether or not this drug had an effect on weight gain. Okay, so now we're looking at this. We say, oh, it's a single set number. Now we have one sample, the differences, and we're going to compare that to the value which represents no effect in terms of the drug. Basically our null hypothesis that our drug had no effect. Okay, well, what would that value be? That value would be 0. So what do we have here? We have another single sample t-test. This is a single sample t-test. But in this case, the number we're comparing this to, the sample of differences that we're comparing it to, is 0. So rather than an independent samples t-test, now we have a combination of a single sample t-test and based on the results of paired samples. So this second example gives us a look at another kind of situation we might find. Number one, they're paired samples. And number two, it's a single sample t-test. We're going to compare the value we get, the mean that we get, to the value 0. Now, what is going to be a standard deviation that we're going to use to figure out the value of t? Well, since there's only a single sample, it's going to be based on the standard deviation of that sample, the differences. Okay, so that's really what happened. You're really doing a new test that doesn't involve the original values at all, but only the differences. Okay, so now let's look at another possibility here. The rats were treated. Let's look at this from another perspective, rather. Okay, the rats in the problem that we just looked at, they were treated with this agent, were significantly less obese than the untreated rats. Okay, in other words, after the treatments were done, after the year, they had lost a lot of weight. Okay, so we know that after the study was done, that there had been some weight loss. Okay, now does that mean that the t-test run that it returned a probability value of greater than 0.05 or probability value of less than 0.05? Well, one of the things that we're doing when we run these tests is we're determining whether or not the probability that we would be wrong if we rejected the test is less than or more than 5%. Alpha is our level of tolerance for being wrong. So if we want to be 95% certain, that means we have a level of tolerance for being wrong, or an alpha of 5%. So we want these two means in terms of standard errors to be far enough apart that we can say with 95% certainty or less than 5% chance of being wrong that that we can say that the means of the populations are different, that we would get that result less than 5% of the time if the two means of the populations were the same. Okay, so how do we determine that? Well, we determine that by calculating a t-score or a z-score. That t-score or z-score represents the probability that we would get that outcome if there were no differences between the two means. We normally call that, when we're talking about it, a p-value. In other words, if we have very large populations and we're going to use the z-table, if we got a z-score of 1.96, we would say that there's exactly 5% chance of being wrong if we reject the null hypothesis. If we got a p-value of 2.5, z-score of 2.58, we would say that there's less than 1% chance of being wrong if we got that value. And we said that the two means were different. Okay, so the p-value represents the real probability that you would be wrong if you reject the null hypothesis. If the p-value were 3, well, I don't have a value off the top of my head I could tell you for 3, but I know that means since it's bigger than 2.58, it's more than 2.58 standard deviations apart, the two, or standard errors apart, the two means. I can say with more than 99% certainty, with a p-value of less than 1%, could be a p-value of 0.0034 or something like that, less than 1%, that we would be wrong if we reject the null hypothesis. If we have that available to us, and programs like SPSS, SAS, and R, for instance, will actually calculate these p-values. If we're doing this manually, well, it's going to be a little bit hard for us to do this, so we'll usually just say, look to see whether it's greater or less than the critical value of t that we need to know that we're at that 5%. We're beyond that 5% barrier. Okay, so let's take a look at this. So we think that there's a significant difference between these two groups. Okay, would our p-value be greater than 0.05 or less than 0.05? How's that a question for you guys? Unfortunately, the answer is right next to it, but I'm hoping you won't read it. Would a p-value of less than 0.0 would a p-value be less than 0.05 or greater than 0.05 if we want to reject the null hypothesis? Take a guess. Somebody out there, take a guess. At least that way I'll know you're still there. Okay, are you guys still there? Can you hear me? Oh, less than 0.05. Thank you. Okay, and the reason why it's less than 0.05, excellent. I think there's a little bit of lag. I don't think it's that you're not answering. I think there's a little bit of a lag that we're experiencing. That's a possibility. There, yeah, it could be. It's less than 0.05. Okay, since the p-value, our real probability of being wrong is less than 5%, less than alpha, p is less than alpha, then we reject our null hypothesis. Okay, all right, so let's see if I can, I think this is something we already went over. Which group was independent? Okay, yeah, I think we already kind of went over that. Yep, I just repeated that. Okay, so let's move on to some actual examples of this. Okay, let me turn this page here so we don't have to look at that silly note. And I'm going to open up a document here. See which one I have here. Okay, here we go. I'm going to give you an example to start off with. I'm going to probably mostly use Excel for this. Okay, so I'm looking at a study where we sampled a group. Group's called X1 for whatever reason. We sampled this. We took values, numerical values. We measured something, blood pressure, blood sugar, or something like that, and we got these various values for it. Now, on the exam, it's highly likely that there'll be some sort of backstory behind this. In other words, describing, like in the examples we just looked at, describing the type of study it was, how the study was done, and stuff like that. And you'll have to parse that down into, what's the important stuff that you have to read there, and what are you actually looking at? Well, in this case, we're looking at a situation where we took a sample from a population, and we want to compare it to a known mean or a known value from another population. Okay, so there's only one sample involved here, so what we're dealing with is a single sample t-test. Okay, that should be pretty obvious at this point, I hope. Okay, so I'm gonna just simply, you can do this along with me. I'm just gonna type these in here rather than send you Blackboard or something like that to download a file. Okay, now keep in mind that in most cases it's going to be hard for us to find a significant difference based on such small values. Let's see, did I get them all? There's 7 values, and I got 7 values. Okay, so now the first thing I'm going to do is I'm going to calculate my mean for that first group. Okay, my mean is 5, so I'm comparing the mean of my sample, that's x bar. And I'm going to compare that to the known mean of the other group, which is 7. Okay, so now in order to do that, I have to determine whether these two values are enough standard errors apart, enough standard deviations for the sample means apart, that I can reject the idea that I would get that big a difference if there were no difference between the mean of population 1, which we don't really know, we don't know it's the sample mean, and the mean of population 2, which we actually do know, which is 7. Okay, so now I need to have a standard error, standard deviation I can work with. So in this case, the only thing I have is my standard deviation for my sample. The sigma for the populations is not known. So my standard deviation is going to be, whoops, I should put that on the other side. Let me put that on that side. Is going to be equal to, I'm going to calculate it, of the sample, okay, which is 2. Okay, so now I need to know, well, that's how variable the individual values are. What I really need to know is how variable from a situation with the variability numbers, how variable would samples from that population be? And that, of course, is our standard error. Okay, and how do we calculate that? That's going to be equal to our standard deviation for our single sample, t-test, divided by the square root of the sample size. Sample size in this case is 7 individuals. Okay, and that's equal to 0.08. So now, in order to calculate what the likelihood of this outcome would be, I'm going to calculate a t-score. Okay, and my t-score, what is my t-score going to be equal to? My t-score is going to be equal to the number of standard errors apart that these two values are. In other words, x bar minus mu, the mean of the population, over, I got to move something over here so I can see, over the standard error. Okay, of course, this is going to be in the parentheses here because we want that subtraction to take place before the division does. Okay, so I'm actually going to do that here. Equals the, let's see, x bar minus mu. I'm going to actually, well, let's do it exactly the way it looks. 5 minus 7 divided by the standard error. What do we get? We get a value of minus basically 2.3, 2.29. Is that far enough apart for this sample size? Remember, the sample size here is also important. The sample size here was 7. So we have to determine now whether that t-value is big enough that our p-value is less than 0.05. And the way that we do that is we're going to go to our t-table. Okay, and what we want is we want to make sure that this t-value is greater than the t-critical. The critical value of t that we need to prove that the p-value is less than 0.05, which is our alpha. Okay, so that's what we're going to do. Okay, so let's get our t-table up. Whoops. Let me get rid of this. Okay, so let's see what we need for a sample size of 7. The degrees of freedom are going to be equal to 6. So 6 degrees of freedom for a 95% confidence interval or an alpha of 0.05 in both tails. This is 2.5 in the right tail and 2.5 in the left tail would be 0.05. So our value is going to be let's see, 6, going to be 2.447. 2.447. So T critical is 2.447. So can we reject our null hypothesis in this case? Any opinions there? I'll wait for a moment while I check to see if there's any lag. No, we can't reject the null hypothesis, right? We can't reject the null hypothesis because we haven't exceeded our critical value at t. So we can't say that this outcome would be so unlikely that it would only occur less than 5% of the time if the two population means were the same. Okay, so we failed to reject our null hypothesis in this case. Okay, let's go back and take a look at another example here. And in fact, in this case, we're actually comparing two populations. Oh, I don't want you to see that. Oh no. Oh, I'm gonna minimize this. I'm gonna open up another version of this, which doesn't show you the answers ahead of time. Okay, here we go. Okay, in this case, okay, we're gonna look at a situation where we sampled two independent. We took two independent samples from two populations, from two groups. Okay, this is the result from group 1, which is the same as we just saw. This is the result from group 2. Okay, so I'm going to fill in another column here. Okay, and this is going to be 12 and 4 and 7 and 10 and 5 and 8 and 3. Okay, happens to be the same sample size, doesn't have to be the same sample size. That's not required here. Okay, so now in this case, I'm going to clear this out. Okay, in this case, I'm going to find the means of both of these groups. Move this over here. Okay, so let's find the means of both of these groups. Okay, and I'll find the average here. And then I'll find the standard deviation. Now, we don't know sigma phi to these groups, right? So this is not applicable. Right? We're going to find standard deviation for both of these groups. I'm going to do one, and then I'm going to copy over the other. Okay, and we're not going to worry about the standard error right now. I'm going to hold off on that because we're going to have some decisions to make. Sample size here is 7. Sample size here is 7. It does not have to be the same necessarily. I'm going to center these here so it makes it easier to read. Okay, so now the t-score, we're going to calculate that in a moment, and so on and so forth. Okay, so now let's see what we know here. Let's copy this over. Okay, sample size. Let's copy this over. I have a tendency to use the menus. There's quicker ways to do this. Okay, so let's take a look now. When we have independent samples, we're going to do a t-test. We know the mean of the two groups, right? Now, I have to look at whether or not I know the standard deviations of the two groups, right? Now I have to make a decision. Should I pool these standard deviations or should I use them unpooled? And that's going to be based on whether or not I believe that they're close enough that I can pool the two standard deviations. There's a couple of ways we're going to do this. In SPSS, there's an actual calculation that it does to help you in determining that. When we're doing this manually, we're basically going to be left to use our judgment for the time being. Okay, so usually you'll pool the two standard deviations if one is double the other. Okay, if one is half the other one. Okay, in this case, one's 2, one's 3.2, 2.3, one's 3.2. So in this case, I'm going to pool these standard deviations. I'm going to assume that the standard deviation for the two populations are the same, so I can base my calculations on a pooled standard deviation that's determined by 14 numbers rather than two groups of 7 numbers. Okay, so now I'm going to need some help doing that. I'm going to have to look up what these formulas actually look like that we're going to use to actually calculate these things. And I think you guys may remember that we have kind of a guideline on here that we use during the lab. Okay, and in this case, this first part over here, we're looking at sample standard deviations that are assumed to be equal. Well, in this case, we're dealing with two populations that we've taken tests from, two populations that we're going to do t-tests with. And we're going to assume that the standard deviations are equal based on these two numbers. Okay, so now how do we proceed from that point? Okay, so now let's go back to take a step back and actually talk about how we might actually solve this problem in real life. The first thing that we would do is we would state a null hypothesis. Okay, what is our null hypothesis going to be in this case? Well, our null hypothesis in this case, oops, let me go down here. H null, I'm going to have two, right? H null and H alt, alternative hypothesis. My null hypothesis is that there's no difference between the means of these two groups. Okay, so I can state that mu1, oops, I'll use lowercase, mu1, the mean, now notice I'm using mu, not x bar, because my hypothesis is based on the populations, not on the samples. I know what the means of the samples are. So my null hypothesis, mean of population 1 is equal to mean of population 2. My alternative hypothesis is that the mean of population 1 is not equal to the mean of population 2. Okay, so now we can get into a couple of variations of that as well. We can there may be situations where you know that the mean of population 1 can only be larger than population 2. So your null hypothesis may be that if you want it, let me redo this so I don't have to change that original one back. Okay, you may be wanting to prove that mu1 can only be larger than mu2. In other words, that this will increase a certain score on some test of knowledge or something like that. Let's say, okay, that the mean of group 1 is going to be greater than the mean of group 2. Well, then your null hypothesis would be, since we already know that it can only be larger if there is indeed a difference, well, then your null hypothesis would be equal to or less than mu2. The equal part is always in the null hypothesis. Because it's a null hypothesis, intuitively you should be able to figure out that, like, gee, equal should be in there if it's null. So this would be our null hypothesis. This would be what we're trying to prove. And in that case, we're only dealing with a single-tailed sample. All of that 5% possible error can be in one tail, right? So for instance, for 95% certainty, you could use only a t-score of 1.64, which would represent one tail having 5% in it. Okay, I'm not going to beat that to death right now because I want to make sure we have time to go through the rest of these. Okay, so at any rate, so that would be a single sample. That would be a, one-sided t-test. So right now what we have here is a t-test for independent samples, two independent samples. We're going to assume that the standard deviations are the same. Therefore, we're going to pool our standard deviations. Okay, so let's go to our formulas. We stated our null hypothesis and alternative hypothesis. Okay, now determine your level of confidence. In other words, what level of accuracy do we want to do this at? Okay, well, let's see where my paper went. Okay, well, our level of confidence is we want alpha, right? Alpha is going to be equal to 0.05. That's going to be our criteria for whether we reject or accept our null hypothesis. That's the same as being 95% confident. Okay, we want to be more than 95% confident, and we want to be less than have 5% chance that we're going to be wrong. Okay, so now in order to prove that, we're also going to compare this to a critical value of t. Okay, well, I'm going to have to calculate what that critical value of t is it's based on, among other things, it's going to depend on the sample size and degrees of freedom. Okay, we're going to be calculating that in a moment. We're going to be figuring out what that might be in a moment. Okay, so let's reference our sheets here. Okay, first thing I want to do is calculate my pooled standard deviation. Well, what is my pooled standard deviation going to be equal to? Well, if you look at this, the pooled standard deviation, SP, is going to be equal to the sample size minus 1. That's the degrees of freedom for that first group, right? Pretty simple, right? So that's 7 minus 1 is 6 times the standard deviation squared of group 1. Okay, well, our standard deviation is 2.3. We're going to square that. We'll calculate that in a moment. Okay, another word for standard deviation squared is the variance. Remember, we got the standard deviation by finding the square root of the variance. We're going to add to that the degrees of freedom for the second group. Now, note we can have two different sample sizes here. Perfectly okay. In this case, it's the same, so this is going to be a 6 also, times the standard deviation squared for the second group, which was 3.2 roughly, and divide that by the two sample sizes added together minus 2, an overall, basically an overall degrees of freedom. Okay, and we're going to take the square root of that whole thing. So let's go ahead and actually do that calculation. Okay, I'm going to go over here, and I'm going to actually calculate my pooled standard deviation. I'm going to put a bunch of rows in here, so I got a little bit of working room. Okay, so let's calculate our SP, our pooled standard deviation. Well, let's see. That's going to be equal to the square root of, and I'm going to try and do this all together here and see if I can get it to work. N minus 1, I'm going to do that right away because it's simple. 6 times our standard deviation 1 squared. So that would be 2.3 times 2.3. Okay, and I'm going to put that into parentheses, and I'm going to add that to, do the same thing with the second group, and that's also 6 times our second standard deviation squared. Okay, and I put that into parentheses. Now I'm going to want to resolve that whole top part as one calculation. So I'm going to put all of that into parentheses. Okay, and I'm going to divide that by the n1 plus n2 minus 2. That's 7 plus 7 is 14 minus 2 is 12. Right? And that division's got just a number over there. It's going to, I already have the top, the numerator all bracketed together. But now I also need to let it know I want to find the square root of all of that calculation. So I'm going to put an extra set of parentheses around there. So if I'm looking, I'm going to hit enter, I'm going to get the right answer. So my pooled standard deviation is 2.8. Kind of makes sense intuitively, doesn't it? It's between the two of those things. So if I look at that and it's not between the two of those things, I'm kind of suspicious that something may have gone wrong. Okay, so now I'm going to calculate my actual t-score. So that's my pooled standard deviation, not my standard error. Now I have to calculate how many standard errors apart are these two values. I can't see the chat box, by the way, in case you're asking me something. Will we still calculate? Let me go back to that, make sure I don't get too far ahead of you. The one we're doing right now is two-sided. Okay, I just gave you an example of what it might look like if it were one side. So pooled standard deviation will still calculate the standard error. Yeah, we're about to right now. Good question. Okay, excellent question. If we look here now, this bottom part is the standard error. Okay, so our standard error, maybe I'll even do that separately. Maybe that's a good idea. Standard error, right? Our standard error is going to be equal to the square root of these. Now this is not one. That's actually a pool. That's a typo. It's the PDF file, so it's really hard for me to change this. That's the pooled standard deviation that we're using here to calculate our standard error. Okay, that's the one that we've agreed on that we're going to use. Okay, that's going to be equal to our standard error times itself divided by, I'm going to put that in parentheses, divided by the sample size, which is 7. And I'm going to add that to our pooled standard deviation. Times itself over the second sample size. In this case, happens to be 7. Right? And I'm going to put that in parentheses also, so it does that operation separately. Okay, so we're going to do this multiplication and division. We're going to do this multiplication and division. Then we're going to add them together. And we're going to finally take the square root of that whole thing. Okay, you can do this in more steps if you want to, so that you avoid making the mistakes that I inevitably seem to make, because I get ambitious with this and try and do too much. Oh, no. Okay, let's see what I did wrong here. Okay, so we got this. Okay, that's good. That's in the parentheses. We're going to add it to this. That's in the parentheses. And we're going to, I'm not sure why it's telling me it's wrong. I got 2 parentheses on the outside here. One in there, one in there. Not sure why it's telling me I'm wrong. I didn't find an error in the formula. Yeah, that looks, oh, no, I don't want that. I want to find, oh, no, well, oh, did I leave out a parentheses at the end? Parentheses, oh, it only needs a single parentheses there. Okay, because that one, well, let's give it a try. Okay, so the standard error is equal to 2.21. I don't trust that. Why would it only need a single? See, now it looks like it's doing the square root of this and then adding this to it. That's not what I want. Why is it forcing me to eliminate? I got 2 parentheses in this direction. Oh, I need an extra parentheses. That's what it is. I'm missing a parentheses here. Instead of taking one away, it should be adding it. There it is. There's our standard error. Did you see what went wrong there? You should always have the same number. I didn't have parentheses at the end here. See, if I count these, there's 1, 2, 3 parentheses on the left, and there's only 1, 2 parentheses on the right. So it needs an additional one. I think I actually took away, yeah. So it needs an additional one to resolve that. So that's our standard error. You guys get the same answer as I did? Okay, yeah, okay, good, excellent. Okay, so now our t-score is going to be the difference in the 2 means, right? The different t-score now is going to be the difference in the 2 means. It's going to be x1 minus x2. Okay, so I'm going to put that in parentheses. X1, which is 5, minus x, oops, left out the equal sign there, equals, parentheses, 5 minus 7. Okay, the direction doesn't really matter here. We're going to use the t-score the same way either way, divided by the standard error. Okay, and again, I had to put it in parentheses so it does the subtraction or addition first before it does the division. And that comes out to be minus 1.32. So I pose the same question to us that we had before. Is that large enough t to exceed the critical value of t that we need for an alpha error of 5%? Is our p-value going to be less than 0.05 here? That's all. Those are all really the same question, and I'll have the same answer. Can I reject the null hypothesis? Is our p-value less than 0.05? Have I exceeded the critical value of t that I need for this particular sample size? Well, how do you determine the number, what the critical t-value is? Well, you need the degrees of freedom, which is for this situation where you're pooling standard deviations, n1 plus n2, which is 14 minus 2 is 12. You would take that 12. You go for your t-test, t-table. Oops, wrong file. Try again. Okay, t-table for critical value for degrees of freedom equals 12 is going to be 2.179. And if I look here, I have not exceeded my critical value of t. So I failed. My p-value is greater than 0.05, not less than 0.05, which is greater than alpha. So I fail to reject my null hypothesis. Okay, so are you guys comfortable with that so far? When we pooled the standard deviations, our justification for pooling the standard deviations was that the two standard deviations for the for this test are not one's not double what the other one is. We need to calculate Q sample, then we calculate, then we compare. We need to calculate the sample. If the t-value that we calculate is greater than the critical value of t, in other words, they're more than two standard deviations, two standard errors apart, for instance, roughly. If they're far enough apart, if that's a big t-value that we calculate, we can say that the two means of the populations are different, and we reject the null hypothesis that they're the same. Okay? If the t-value comes out small, right, then that's basically saying the two means are not very far apart as far as we can tell. So we can't reject the null hypothesis that the two means of the two populations are the same. So we need to exceed the critical value of t, which we get from the table, in order to say we can reject the null hypothesis. Okay, so let's go on to another problem here. If I can get to that document. Wherever I put it. Here we go. Okay, so let's take a look at number 3. Okay, let's see. Independent samples. Okay, in this case, I am looking at. Let me see what I had meant to do here. Okay, in this case, I am looking at not independent samples, but let's say I'm looking at a situation. I meant to put paired here. Let's say I'm looking at a situation where I'm looking at values that were determined for a test subject before an intervention and after an intervention. Maybe these are scores on a some sort of test of the effects of some drug. Okay, and this is the same individual before they took the drug and after they took the drug. Okay, so we want to see if they showed an improvement being a lower number on this test, and if we can say that that was not due to chance, that the difference in the between these two groups is not due to chance. So this is really x1 after. Make it a little clearer after, and this is x1 before. Okay, so I'm going to enter these numbers in Excel. Let's see if I can get really lucky and get it to just paste in. Okay, let me scroll up a little here. Okay, yeah, that worked out pretty well, except for that one. Let's get that one over. Okay, so these are values before and after, but for the same subject. In other words, if I added another column here, right, this might be subject number 1, number 2, number 3, number 4, and number 5. Okay, so what I'm really interested in here, whether or not there was an improvement for each patient. And this gives me much more power, because if you can imagine, if I were looking at a group of people that were independent, that weren't the same people before and after, well, this person and this person, they could be vastly different, have vastly different weights, heights, BMIs. One could be a smoker, one could be a non-smoker. There's so many variables between what might be going on with these different test subjects if they're different, if they're two different groups of people. Then, if I'm looking at the same person, the person's overweight here, they're overweight here. If they're a smoker here, they're a smoker here, and so on and so forth. You can eliminate a lot of variables when you're doing that. Okay, so we have a certain advantage when we do a paired sample t-test like this. So in this case, what we're really interested in is not so much what the actual values were starting, but what the differences were, right? The differences are really what's most important to us here. Okay, so let's look at what those differences are. Whoops. So those differences are, okay, it's 15 minus 3. Okay, comes out to a difference of 12. So I'm going to copy that down. Okay, most of these people showed an improvement. I'm going to change 1. Just so, oops, changed the wrong number there. Okay, I'm going to change this one to 6 and this one to 7. Because, that's the way things are in real life. Occasionally, somebody will be a bit different. So our expectation is that if there's no, so what would our null hypothesis here be? Right? Our null hypothesis is going to be that there's no difference between the performance of these test subjects before and after this intervention. So our null hypothesis is that that basically that the means of the differences are equal to 0, that there's no difference. And our null hypothesis, our alternative hypothesis, is that the means of the differences are not equal. If we did this for the entire population, the means of the differences would not be equal to 0. This could be also a one-sided t-test where you're going to assume that, well, it couldn't be higher after we didn't do anything. If we trained them or if we did this intervention, a diet change or something like that, we don't think it could be high. We don't think it could possibly be higher. So we might say that the means of the differences are either less than or equal to, and then the alternative would be that they're greater, that they're less than or greater than, and that the alternative is that they're less than, the less than 0. Excuse me. So that actually, you want to know which way probably would have made more sense to do this would have been the after minus the before. Right? It's going to work the same way. This is a little bit more intuitive. We can see that there was a drop there. Okay. And again, we could look at this as a one-sided test if we made the assumption that whatever this marker is, it's that it could only go one direction for the mean of the population. Obviously, one guy went the wrong direction, so it can't be for every individual, but overall, would only go that direction. Okay, so how are we going to analyze this? Well, basically, we only have a single sample here now, right? So basically, this is a form of a single sample t-test. So to go through that very quickly, the mean difference is going to be equal to the average. Okay, and the standard deviation of the differences is equal to standard deviation of all these values. And the sample size is 5. And the degrees of freedom is equal to 4, 1 minus that. Okay, and my standard error, which I'm going to need to actually calculate my t-score, is equal to the standard deviation divided by the square root of the sample size, which is 2.89. Okay, so now my t-score is going to be equal to, what's it going to be equal to? Well, in this case, it's a single sample t-test, and we're comparing the value we get for the differences to the value 0. So our first value is going to be our x bar minus what would have been mu, but in this case is just simply 0 because we're comparing it to 0. So it's really just going to be the value of x bar, the differences, divided by the standard error. Okay, so we get a value of minus 2.7. So with a t-score of minus 2.7, do you guys think I can reject the null hypothesis here? Have I exceeded my critical value of t? Oh, okay. We got somebody that's voicing an opinion. Laura, did you check the t-table to see what the critical value was for a sample size of 4? Aha! Okay. Actually, I think you're right. However, I didn't mean. I'm so sorry I trapped you like that. But let's look it up. See, that's that. Now you would think, but it's such a small sample size that the t-score could be pretty big, right? Okay, so let's see what critical value for 2.776. Okay, is my critical value 2.776. Remember, these are absolute values. We're not really worried about the signs. We fail to reject our null hypothesis. Exactly right. That's a very small sample size. So T critical is 2.776. We're very close. Our p-value, if I had to guess, our p-value might be like 0.06 or something like that. Not quite 5% chance of being wrong. We have a 6% chance of being wrong because we're a little bit bigger than a little bit smaller than the t critical. So since we're not smaller than 0.05, we fail to reject our null hypothesis. Okay, so now